Welcome. This lesson is on electric potential due to point charges, which is a subtopic of electric potential and electric potential energy in Unit 18 Electric Fields. By the end of this lesson, you should be able to understand how the concept of electric potential leads to the electric potential energy of two-point charges, and use the equation EP equal to QQ over 4 pi epsilon 0 r. Imagine a point charge positive Q produces an electric field around it. We call it the source charge. A positive test charge small q is placed at infinity. At infinity distance, the test charge will not be affected by the electric field created by the source charge. So, the electric potential is defined to be zero at infinity. Assume the test charge is moving at a constant velocity towards the source charge. When the test charge moves closer to the source charge, it will experience a repulsive electric force from the source charge. So, without changing the velocity of the test charge, an external force that is equal and opposite to the electric force is applied to move the test charge to a point at a distance r from the source charge. In the process of moving the test charge from infinity to the point, without changing in velocity, there is no change in kinetic energy of the test charge. The work done by the external force is transferred to the increase in the electric potential energy of the test charge. This can be written as the equation, the work done by the external force equal to the change in electric potential energy. The change in electric potential energy is equal to the final electric potential energy minus the initial potential energy. The initial electric potential energy of the test charge at infinity is taken to be zero. Then, the final electric potential energy at the distance r from the source charge is equal to the work done by the external force. From the previous lesson, we've learned that the work done by the external force equal to k times the product of the source charge and the test charge over r. Hence, the electric potential energy of two-point charges is given by k times the product of the two charges over their separation. K times the charge capital Q over r is the electric potential at the point a distance r from the charge. Hence, the electric potential energy of the other charge small q at the point can be written as the electric potential times the charge. When we use the above equations to calculate the electric potential energy, the sign of the two-point charges required to be included during the substitution of values. So, if the two-point charges are unlike charges, they will attract. The electric potential energy is negative. If the two-point charges are like charges, they will repel. The electric potential energy is positive. Let's try some examples. Please pause the video to try the question. In this question, both the particle and the sphere are positively charged, they would repel each other. So, energy is required to bring the particle toward the sphere. This energy is taken from the kinetic energy of the particle. So, when the particle is moving towards the sphere, the loss of kinetic energy is transferred to the increase of the electric potential energy of the particle. If the kinetic energy of the particle is equal to, or greater than, its electric potential energy at the surface of the sphere, then the particle will reach the surface of the sphere. The kinetic energy of the particle can be written as half mv square. And the electric potential energy of the particle can be written as the charge of the particle times the electric potential at the surface of the sphere. Rearrange the expression, we have the speed of the particle is greater or equal to the square root of 2 times v times q over m. It's given in the question, the electric potential at the surface of the sphere is 470 volts. The ratio of charge to mass is 9.58 times 10 to the power of 7 coulomb per kg. Substitute the values into the expression and calculate, we get the speed of the particle is greater or equal to 3 times 10 to the power of 5 meters per second. It means that, if the speed of the particle is greater or equal to 3 times 10 to the power of 5 meters per second, then the particle will reach the surface of the sphere. In the question, it's given, the speed of the particle is 2.5 times 10 to the power of 5 meters per second, which is less than the minimum speed required to reach the surface of the sphere. So, the particle will not reach the surface of the sphere. Let's try another example. Please pause the video to try the question. Recall that the electric potential energy of two-point charges is given by K times the product of the two charges over their separation. Given in the question, particle Q has electric potential energy equal to negative 8.16 times 10 to the power of negative 19 joule. The electric potential energy is negative, so the two particles are unlike charges. One of the two particles carries a negative charge. Then, the product of the two charges is negative. Given the magnitude of the charge on each of the particles is 1.6 times 10 to the power of negative 19 coulomb. So, the product of the two charges is the negative square of 1.6 times 10 to the power of negative 19 coulomb square. Substitute the values into the equation and calculate the separation of particles, which is 2.8 times 10 to the power of negative 10 meters. We have come to the end of this lesson.